consider for a moment the function f of x equals x cubed minus 8 divided by x minus 2. And if you were to sketch this curve or graph this curve, it's going to look like a parabola, which may surprise you at first until you recognize that the degree of the numerator is 3 and the degree of the denominator is 1. So when that divides out, it'll divide down to a quadratic. And depending on how much attention you're paying, you may or may not notice that there is an issue with this graph at the point x equals 2. Specifically, that the function's not defined at x equals 2. X, in fact, can't equal 2. And so we would say that there's a hole in this graph there. But we can consider this graph and ask some questions about what's happening, or what is the behavior of the curve around x equals 2. So there's a table in your notes. So go ahead and fill out that table to look at what's happening around 2. And just use your calculator, graph it, use the table feature, don't do it by hand. Take a moment and fill out that table, what's happening around 2. Now that you've taken the time to fill out the table, it should be obvious to you that as x gets closer and closer to 2, f of x is getting closer and closer to 12. Formally, we would say something like this, that the limit of f of x as x gets closer to 2 is 12. And instead of writing this sentence every time we want to express that idea, mathematicians would write it this way: the limit as x approaches 2 of f of x is 12. Informally, what we mean by limit is what is happening to y as x gets closer to a certain number. Now, one thing that's important and that you should notice in this table is that in order for a limit to exist, the y values must be approaching the value from either the left or the right side. From either the left or right side, we should get closer and closer to 12. Or we would say that the limit does not exist, D and E. So notice in our table that from the left-hand side of 2, it's getting closer to 12. And from the right-hand side of 2, the values are getting closer to 12. If they were approaching different values from each of the two sides, we would say there is no limit. Now sometimes we would say things like, from the left, the limit is this. And to note the left-hand limit, the notation is the limit as x approaches 2. And if we're coming from the left, we'll have a little minus sign or negative sign above the 2. And that just means from the left-hand side of 2. Right? As you go 1.8, 1.9, 1.95, 1.99, so on and so forth. And if we were talking about what's happening just on the right side, instead of a minus, we would use a plus sign. The limit as x approaches 2 from the right of the function. So as we look at 2 going from 2.3 to 2.2 to 2.1 to 2.05, we are approaching 2 from the right side of 2. Please make note of this. In order for a limit to exist, the left-hand limit and the right-hand limit must be the same. Again, in order for a limit to exist, the left-hand limit of our function must equal the right-hand limit of our function. And in this case, c is just some random x value where we happen to be looking. If these two limits, the left and right-hand limits, are equal, then we would say that the limit at c of f of x is whatever that number is. In our example we did earlier, it was 12. Generally, we're using the letter L, so just to represent the value of the limit. Let's consider a different example. In this example, we have a graph that really is made up of two parts. We've got a diagonal line on the left-hand side of one and a horizontal line on the right-hand side of one. And we could talk about the limit from the left-hand side of one of whatever this function is as being 1. Because the y values, as we approach the x value 1 from the left, the y values are getting closer and closer to 1. But if we considered the limit of this function, that's bad notation. If we consider the limit of this function as x approaches 1 from the right, we would say the limit is 2. Because if you consider the graph, if we started at 3 and moved to 1 on the x-axis, our y values are 2 all the way. The left-hand limit is 1 and the right-hand limit is 2. This means that the limit as x approaches 1 of our function does not exist, because it's going to two different numbers on the left and on the right. And the limit is different from the function's actual value. Notice that the limit does not exist, but this function has a value at 1, and it is 2. Right? And that's noted in the graph by the closed circle, that when x is 1, the function's value is 2. And this is an important thing, that a function may not have a limit even if it is defined there, and that the limit of a function is different from what the function's actual value is. Again, the limit of a function can be different from what the function's actual value is. Let's consider a different example. Here is a different function, and from the left, the limit as x approaches 1 from the left of this function appears to be -1, because as our x values from the left get closer and closer to 1, the y values are getting closer and closer to -1. Then on the right-hand side of this function, or the right-hand side of 1, the limit as x approaches 1 from the right of our function is +1. Because as the x values get closer and closer to 1, the y values are getting closer and closer to 1 as well. This means that the function does not have a limit, or the limit does not exist at 1, because the left-hand limit and the right-hand limit are different. But we can see in the graph that f of 1 is 0. And again, to emphasize, the limit of a function and a function's value do not have to be the same. and the limit at a particular point exists only if the left-hand limit and the right-hand limit are the same. Let's consider a different example. This will be example 4. Here in example 4, we have what appears to be maybe an absolute value graph with a hole in it. And the limit of this function, as x approaches 1 from the left, is 1. Because as our x values start at, say, -1 and move closer and closer to +1, the y values are getting closer and closer to 1. And in this case, the limit as x approaches 1 from the right of our function is also 1. Because if we started at, say, x equals 3, as x gets closer and closer to 1 from the right, the y values are also getting closer to 1. This means that this limit exists. The limit, as x approaches 1 of this function, is 1, because the left-hand limit and the right-hand limit are the same. But notice that for this function, f of 1 is defined to be -2. So when we're considering limits, we have to consider what's happening on the left-hand side and on the right-hand side, and a limit is distinct from a function's actual value. Let's consider example 6. Example 6 appears to be some type of conic section, maybe. Notice that there is a vertical asymptote at x equals 2. And so this creates a picture for us of the limit. The limit of this function, as x approaches 2 from the left, is positive infinity. And some would say it does not exist. And I'll talk about the difference in a moment. I say positive infinity. And the reason it's positive infinity is because as the x values get closer and closer to 2, the y values are increasing without bound. And I would say that the limit as x approaches 2 from the right of this function is negative infinity. And the reason I would say that it's negative infinity is because as the x values get closer and closer to 2 from the right, the y values are decreasing and becoming more and more negative, and just going to continue to be more and more negative. Now, some people in this case would say does not exist, and the reason they would say that is because their definition of a limit is that a limit must be a real number, and infinity is not a real number. For purposes of our class, I will accept either does not exist or infinity or negative infinity. Personally, I think about it including infinity as a limit. And for purposes of the AP exam, you can have either answer. So whichever you prefer, but I will always use infinity and negative infinity. But there's no consensus in the math world on this. But it comes down to the definition of a limit either includes only real numbers or will include non-real numbers such as infinity. Since the left-hand limit in this example and the right-hand limit in this example are different, then the limit as x approaches 2 of f of x does not exist. Now, this is a problem with the way I define things. A limit, we would say, if they were both going to infinity, also does not exist. And this is where the folks that use do not exist are probably more consistent. And as I say that, I will probably make the adjustment that I'll always say does not exist if we're going to infinity or negative infinity. but there's no consensus. You can go either way, a left-hand limit and a right-hand limit in terms of the AP exam. Infinity or does not exist is sufficient. Finally, this function is not defined at f of 2, so we would say f of 2 in this case does not exist. So we've considered limits and the idea of a limit informally as simply being what are the y values getting closer and closer to as the x values get closer and closer to a specific x value. The last thing we need to talk about is this idea of what happens to y as x gets infinitely large, or what is the limit as x approaches infinity of some function, or what is the limit as x approaches negative infinity of some function. Now, this is in a lot of ways simply a thought experiment. What does it mean to approach something with no magnitude? It's so massive, it's so large. Approaching infinity is not the same as approaching 10. Approaching anything finite is not the same as approaching the infinite. So, some things to consider when we're talking about the limit as x goes to infinity or negative infinity. You could have a curve graphically that as x, like a parabola, that as x gets bigger, y just keeps growing without bound. The limit just keeps going to infinity. Or you could have a cubic that as x gets bigger, y keeps getting more and more negative. We would say the limit of this function is negative infinity. Or you could have a curve that levels off a bit. Maybe something that as x gets bigger, like a logarithmic curve, or a square root curve, or even just some weird function. It's approaching some horizontal boundary that it'll never get larger than. All right, so as x gets bigger, y values are approaching this horizontal asymptote. Right, it can level off. So in this case, where it's approaching some horizontal asymptote, the limit as x approaches infinity is some value. A final example is our curve could just continue to oscillate back and forth between two things. So it's never really approaching anything. And so this would be the case where the limit does not exist, because it's just kind of bouncing back and forth between two things as x gets bigger and bigger. Maybe between being positive and being negative, as an example. So there we have our beginnings, the ideas of limits.